This is a street sign. Even though it is a street sign with its content written in Russian, at the base level, your brain knows it is a street sign. This, and these are also street signs. Even though their contents are written in different languages, your brain has no trouble recognizing the fact that they're all street signs. This is why when you go on vacations to new places, you can effortlessly tell that you are in a different location and decide how you intend to explore the local sights and sounds. The human brain effortlessly makes the connections to recognize the similarities that define a street sign while also recognizing that the content on the signs is different. With recognition comes decision making. If your brain cannot translate the words on the street sign, it informs you to either ask the locals or use Google recognition and translation applications. That is decision making. So, without a thought, your brain has helped you recognize a new location in real time, and the translation app has recognized the relevant patterns needed to translate the street signs into a language you understand. Now the question is, how do these intelligent connections and inferences happen? The short answer is that, quote and unquote, something in that visual cortex and smart brain of yours recognizes the street signs for what they are. And that same thing has been integrated into the translation application on your phone to recognize languages and translate them. That something is the neural activity in the human brain, and the use of neural networks in inanimate systems mimics that activity. So, neural networks are inspired by the human brain. Neural networks mimic the behavioral patterns of the human brain to infuse machines, applications, and systems with artificial intelligence. Neural networks are trained using data to make intelligent decisions. Neural networks have the potential to dramatically simplify and improve simulation applications in cases where complex decision logic is required. As an example, consider a typical manufacturing application where we must select between 2 or more production lines in a factory, where each line consists of a dozen workstations in sequence, and we would like to select the line that can complete the job the soonest, i.e. smallest make span. Factors that influence the current make span for a line include status of downstream workstations, where the amount and type of work at each workstation impacts the completion time. The downstream workstations along each line might have sequence-dependent setup times as well as work in progress, all impacting the decision regarding which line can complete the job the soonest. Knowing how to consider all these factors and construct a good rule to select the best line is difficult. Using neural networks, it is possible to bypass this whole process of building complex rule-based logic and have the logic be automatically created for us by the simulation model. We add a neural network to the model to make the decisions and train the neural network using simulation data so that the model gets better and better at making the correct decision over time. Hence, we not only avoid having to build the complex rule logic into the model, but also have a rule that learns and improves over time to optimize the system performance. Hence, the incorporation of neural networks into simulation is a game changer for optimizing systems with complex decision logic. So, what is a neural network? Neural networks are a type of machine learning algorithm that have been successfully applied to a broad set of problems. These applications include analyzing text, speech, recognizing, classifying images, anomaly detection, pattern recognition, and regression models for predicting values. Examples of successful applications include Apple's Siri for recognizing and responding to voice requests, and image processing in self-driving cars. Our focus will be on the use of neural network regression models for predicting values for use in our model's decision logic. We will describe the standard feed-forward regression neural network for predicting output values, but there are other variations with special applications. In simple terms, a neural network maps a set of numeric inputs into a set of one or more outputs. In its most basic form, we have a single node called a perceptron, also called a neuron, with a set of inputs, x's, a weight w assigned to each input, a bias assigned to the node, an activation function f following the node, and a single output y that is computed from the inputs, weights, bias, and activation function. The output is a predicted value that the perceptron is making based on the current set of inputs. The following depicts a perceptron. The predicted value y is calculated as f parentheses w1 times x1 plus w2 times x2 plus wn times xn plus bias, close parentheses, where f can be any function. In words, we sum the weighted inputs, add the bias, and apply the activation function to get the predicted value. To apply this model, we need to determine the values for the weights and the bias so that the perceptron generates the correct predicted value. For example, if we are using the perceptron to predict the selling price of a house based on the square footage of the property, number of rooms in the house, and the year it was built, we select the weights and bias to produce a predicted selling price that closely matches actual selling prices. To do this, we go through a process referred to as training the model, where we take historical data with the specified inputs and selling price and apply a training algorithm that calculates the weights and biases that minimizes the error between predicted and actual selling price. The quality of our prediction engine is therefore heavily influenced by the quality of our training data. One of the big challenges in the application of neural networks is having sufficient high-quality training data to train the neural network. This is where the merger of simulation and AI is most powerful, since a high-fidelity simulation model can generate unlimited amounts of synthetic training data for the neural network. A neural network builds on the basic concept of a perceptron by combining multiple neurons into a layered network, comprised of an input layer, one or more hidden layers, and an output layer as illustrated below. The neurons in the input layer, as the name suggests, define the input data for the prediction engine. The hidden layers are typically most of neurons in the network and provide the core nonlinear data manipulation to get the desired predicted values. Networks with at least two hidden layers are referred to as deep neural networks. Let us now return to our previous example of using a neural network to select between two or more candidate production lines, and discuss the problem of training our neural network based on simulation-generated data. In this example, we use our neural network to predict the make span for each candidate production line and select the line with the smallest make span. At the time we make this selection, we record the neural network input values that were used to predict the make span. Within our model, the entity continues down the selected production line, and then at the end of the line, we record the actual make span. The neural network input values and the model-based actual value are then saved off as training data for our neural network. Model-generated synthetic training data is the key to unlocking the concept of self-trained neural networks for decision logic within a simulation model. To close things off here, it is important to note that neural networks currently play important roles in evaluating industrial processes. Industry 4.0 applications such as simulation and digital twin modeling software are key enablers of AI. Simulation and digital twin modeling software such as Simio provides embedded support for the use of neural network for decision-making within a model. Simio allows users to create feed-forward neural networks directly in Simio without any coding required. The neural network features in Simio are designed to support the use of neural networks for decision-making within the model, as well as the recording of synthetic training data. The neural network model may be trained using Simio's built-in trainer, and then the neural network model can be used in the model logic. Alternatively, Simio allows a user to import an ONNX file of a trained neural network. ONNX is an open, standardized file format for representing machine learning models that enables models to be transferred between AI frameworks. Neural networks add artificial intelligence to Simio models, and these models become smarter over time from training with synthetic data that is self-generated by the model. The training data you generate within Simio can be exported to third-party programs to train your other machine learning models whenever you choose.